Hi, everybody. This is Mr. Folly, and welcome to podcast 1.1, where we will learn about density, states of matter, and mixtures. So let's hop right into it. And welcome back to school. Welcome back. Welcome back. Welcome back. So here we go. Okay, now it won't change. There we go. Physical changes. A physical change is a change in mass. That means kind of like weight. I know there's a difference, but for us, it's close enough. Shape, but not identity. So if I have butter and I cut it, or I boil it, or I melt it, or I freeze it, or I mold it, or I shape it, it's still going to be the same thing. It starts out as butter, ends up as butter. Okay. So here's boiling oil. If I dump boiling oil on the people climbing up, it's still going to hurt them, but it's still going to be boiling oil. It might stop boiling soon. So I change the shape of the clay into voodoo dolls. Voodoo dolls, look, it's Taher. And the attack begins. Chemical changes is change the identity after the change. So whatever happens, you start out as one thing, you end up as something else. It'll have a new chemical formula. For example, if H2O turns into H2O2, that's something different. This is water. This is hydrogen peroxide. Don't drink that. That's bad for you. It's bubbly and all kinds of stuff. So examples of verbs that mean that, I suppose, are burn, dye, precipitate, form a gas, change color. Now, form a gas is not boiling. Okay, so boiling forms a gas, but it's not a chemical change because if I have liquid water and I boil it, it's still going to be H2O. Okay, this is a precipitate. These are leaves changing colors with all the different types of leaves that you should know. And then if you burn Freddy Krueger's face, 1, 2, Freddy's coming for you. His skin is not the same. That's not the same as the skin it started with. Okay, but if he slices you with his little finger knives, that's a physical change because it's still the same thing. If he cuts off your arm's still on. Isn't Freddy Krueger a wonderful example? Pure substances. Elements have one type of atom. Okay, so those things in the periodic table, you have one type of those. So only hydrogen, only carbon, something like that. Elements can be diatomic, and you need to know what these are. You likely forgot them. I'll put the twos on there. They are what I call honkle breath. A little curve. Not that I had to curve, but I just ran out of space. Okay. You need to know these guys are always doublets as opposed to everything else. Like iron is iron 1. Carbon is carbon 1. Calcium is calcium 1. Compounds are more than one type of atom, but they're not a combination of properties. They have new properties. Okay. So if I have water, H2O, if you put a fire to both of these, if I add this to fire, this one explodes. Boom, 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 boom. This one burns. But if I add fire to water, it puts it out. Oh, extinguished. Ooh, big word. Okay. If I breathe oxygen, I survive. If I breathe hydrogen, my voice gets all kinds of squeaky. Sodium will burst into flames if you put it in your hand. Chlorine will burn out your lungs, chemically burn out your lungs. But together we have salt, which is oh so yummy and goes on all of your Bosco sticks. So totally new properties. These are new properties. You wouldn't be able to tell what the parent ones come from. Mixtures. Any state of matter and any state of matter is possible, except we can't really have a solid in a gas much. Homogeneous mixture is called a solution, and every sample would be the same. So an example of this would be if I have XO, 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 OX, OX, OX. Boy, I'm just kissing all of you like grandmama. XO, XO, XO. Oh, sweet. But every sample is the same. So however I cut this up, I'm going to have the same ratio of X's and O's. Heterogeneous, the samples are different. Okay. So a homogeneous mixture is called a solution. Examples are salt water, air, believe it or not, because we breathe in air mixes so quickly that it becomes a homogeneous solution. But every sample has to be the same. Heterogeneous samples are different. So that would be Oh, I love. I want to give you hug, 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 kiss, 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 hug, 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 kiss, 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 kiss. So that would be different. Okay. On these pictures, they are either unevenly distributed or layers. Okay. Unevenly distributed. My hand is getting worse. Unevenly distributed would be something like this. Living things are heterogeneous mixtures. Saltwater, salad, grass, 18 karat gold. Genius. Now this homogeneous, whether it's homo or heterogeneous, is relative. So I could look at skin and go, oh, your skin is a homogeneous mixture, and then so it's homogeneous to the, oh man, I haven't drawn an eye in a while. How do you draw an eye? Anyway, homogeneous at the eyeball level. Hey, that's almost there. At the eyeball level, but skin is heterogeneous under a microscope. Okay. So this is a pure element. This is a hetero mixture because see how it's got layers. Okay. This is hard to see with it, but this is, I would say, it's a homogeneous mixture because it's got a little circle and a big circle, and it's pretty much evenly distributed. Okay. This would be a pure compound. And so what's the difference between this guy, between C and E? See how these have touching parts? If they're touching, it makes it a compound. Okay? You could tell they're in love. They're touching each other. You can tell they're in the same room. This would be a pure element, one type, not touching. This is what I was talking about with a diatomic element. Oh man, that's a word. This would be a diatomic element, and that would be pure as well. Okay. I'm going to skip the rest of this. How to measure? All instruments have a numbered, an unnumbered, and an estimation. Digital ones provide the estimate. Okay. Now that estimate is significant. Okay. Go back. So the estimate is significant. Okay. So if I put a mark right, no, it doesn't want me to measure. It doesn't want me to measure. If I put a mark right here, that would be 8.2, and then I need an estimation. It's clearly past the 2, 8.23. Okay. If I had something right here, smack dab on the 9, it would be 9.0, right on that. I need that other estimation of 0. Okay. If somebody said that was 8.99, they're not crazy, right? Yeah, you're stupid. That's kind of a matter of opinion. But this last digit is significant because everybody in the world will be evenly distributed. Okay, everyone will think that's right, except for maybe. So numbered, unnumbered, and estimation. Numbered part 15 or 20, unnumbered part in there, and then you need one more digit. You can separate mixtures in a couple of different ways. Separation by boiling point is distillation. So what happens is this is my mixture, and I boil it. You're going to have to draw a picture of this or interpret a picture of this, so you should draw this. So this is my mixture, and a hot plate, so I boil it, and the low BP, I just misspelled low, and the low BP thing comes up, and what's left is the high boiling point. BP stands for boiling point. That's the temperature where it boils. Okay. So example of this would be salt water. If you boil it, right? So if I did my little question thing, I hope you know, well, that kind of looks like an animal, that I would be left with salt here, and my drip, 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 drip here would be water. Just to give you an idea how it works. Boom. Density is love. What I mean by that is we need to know the formula for density. Density is a heart with a knife through it. That's the formula. So density is mass over volume. And watch the units. They're changeable, but you have to have whatever your mass unit is, has to be the top density unit. Whatever your volume unit is, has to be the top volume. So for example, it could be milligrams per liter, could be my unit for density. That would mean that milligrams is my mass unit and liters are my volume. More dense things sink. Saturn's density is really 0.687, which is kind of low. Water's density is 1. That means Saturn floats on water. What? That's so crazy. But you need no more dense things sink. It doesn't have to be based on water. Separation by filtration. Filtration is based on particle size. A smaller filter, you can separate a lot of things. It used to be that you cannot, this is still true, filter, whoops, filter a solution. Let's get back there. Hey, that means we're almost done. Get back. A solution. Come on. Solution. So, not, let's just say salt water is unfilterable. So, for example, they talk about the filters in your refrigerator. If you put salt water and try to filter it with that would still be through. Oh, come on. Separation by chromatography. There's two types of chromatography. So, separation by solubility and size for the paper. So, this means that if this is my thing I'm starting with right here, it will be fast if small. And number 2, loves the solvent. And this would be water, or this would be whatever the solvent goes in. And then, oops. And the other one is if it doesn't love the paper. And the love I'm using right now is chemically attracted to. Okay. So I shouldn't say love, I should say if it's chemically attracted to the solvent, if it's chemically attracted to the paper. So if you're looking to ask somebody at the homecoming dance, say, hey, I'm chemically attracted to you. And then you can hang out and play World of Warcraft with the AP Physics kids. So, where else am I? Okay. They will ask you to find this RF factor. Okay, the RF factor is like a retention factor, meaning how slow does it make it go. So for substance A, right, which is the top edge. So when you have a dot that moves, it does get longer and does weird things. You measure it. Excuse me. What you want to do is you would measure the average, take the middle of your dot. Okay. So you're going to take the middle of the dot. So the top part of the dot is A. The bottom part of the dot is B. You're going to find the average of that. So see A plus B over 2. That's your average of the dot. And then you're going to divide it by the solvent front. Okay. Front is a weird word for it, but the solvent is just a liquid. You'll see where the paper gets wet, and that's it. So what you're going to do is, so basically it's the middle over the wet. Okay. And that's the RF. That's the retention factor. Okay. There's another type of chromatography which possibly could ask about, but I don't think they will, which is gas chromatography. So, I'm sorry, this is column chromatography. So what happens is you have your sample and you let it settle out. And as it settles out, you see how there's 3 parts? Then what you do is you open this up and out comes the green boogers, and then you're left with the itchy scratchies and the circles. And then you can, once you have that poured out, then you can pour off the itchy scratchies and just be left with the circles. We all saw this. It's the end. Woohoo! Physical change stays the same thing. Chemical change changes the identity. No distillation, chromatography, and filtration. No elements, compounds, and mixtures by picture. Touching is a bond, which makes it a compound. That's my abbreviation for compound. And that's my end. Toodles.